Hi, I'm Rohit. This is second lab of EE533, and on the screen you are seeing a schematic view of a full adder circuit. And using this full adder, I have built a 8-bit adder. Uh, yeah, this is a schematic view of a 8-bit adder. As you can see, I have used 8 full adders and connected it back to back. And here are the connections. So let me and simulate this 8-bit full adder. Yeah, this is the test bench for the. Yeah, as you can see, this is the waveform of the 8-bit ladder. And the next part, have built the synchronous uh, adder using a full ladder. Yeah, but before that, I'd like to show the 32-bit ladder. Yeah, this is 32-bit ladder designed using 4 8-bit ladders. And using this 32-bit ladder, we have designed a 32-bit synchronous adder. This is my uh, adder. This is the 32-bit adder, and as you can see, the inputs are connected to the flip-flops, and the outputs of the flip-flops are connected to the adder. And similarly, on the output, the output of the adder is given to the input of the T flip-flops, and the output of the T flip-flops is or the registers is taken as the connected to the output. And this is my test page, and let me simulate the test page. Yeah, this is a waveform of the synchronous 32-bit adder. And you look at, yeah, so the first 2 clocks won't get the valid input, and from the third clock onwards, we get the valid output. So here is my inputs A, B, and C, and it's my clock signal. So as you can see, uh, the output is changing at the every pause edge of the clock. And using 32-bit full adder, we have designed a 32-bit subtractor. Okay. Uh, in case of subtractor, uh, uh, we can use the adder to achieve the subtraction functionality. Here I have inverted B. Here I have inverted B and to the adder I've given 1 as C. So this will so the output will be A plus B bar plus 1. So which is the 2's complement of B. That means like A plus 2's complement of B plus 1. So we'll get the subtracted value in the form of 2's complement. And next, take you through the bitwise, and this is the circuit for bitwise AND operation, where the output is nothing but the AND of uh, both the inputs. And just like full bit, just like 32-bit adder, we have used 4 8-bit bitwise AND operator to build a 32-bit uh, bitwise AND operator. And this is a 32-bit bitwise AND. And similarly, I have built a 32-bit bitwise OR operator using 8-bit OR app bitwise OR operator. Yeah, this is my 8-bit bitwise OR operator. Yeah, and using full adder itself, I have built the shifters like 1-bit left shifter. So if we give like for the adder, if two inputs are the same, we'll get the output will be 2A, which is nothing but left shifted of 1-bit left shifted value of A. So this circuit will give a left shifted value of A by 1 bit. And this is my test bench for shifter. Yeah, this is my input, and the output is one bit left shifted value of the input. And similarly, this is a test bench for 32-bit device, and let me run that. Yeah, this is a simulation result of bitwise and currently I'm running the test bench for bitwise or yeah, this is a simulation result of bitwise or yeah. So let me do the mapping for 32-bit synchronous adder. Making my synchronous adder as a top level design. Yeah, this is the mapping report. As you can see, uh, the utilization percentage, like 94 flip-flops were used and 32 4 input LUTs lookup tables were used. And coming to the next part, which is ALU using Verilog. So this is my ALU, like Verilog code for the ALU. So currently I have like five operations supported. Uh, One is addition, subtraction, and left shift, bitwise and bitwise or. So let me run the simulation for this ALU. Yeah, this is a waveform for the ALU, and you can see these are like two inputs A and B. And, these are the outputs of the ALU out and carry. And these are like two variables that I've added in the test bin. So let me integrate those. Yeah, as you can see, first opcode 0, where the two inputs will be added, and the next opcode here, the output is the subtraction, like output is A minus B, and here it's the shift, shift like left shift of operand A, and here it's bitwise and as uh, as you can see, the output is bitwise and of both A and B, and here the output is bitwise OR of both A and B. Yeah, thank you. This is all about the lab 2, where uh, design adder, bitwise and bitwise or shifter, ALU, all in schematic, and I tested and simulated all of them, and also ALU in Verilog. Thank you.